Hello and welcome. I want to thank you for the opportunity to present and discuss today. My name is Brandon Wallace. I'm with BRD Noise and Vibration Control. I started my career out in the HVAC industry, spent about 10 years there, and have now been in the acoustics market for a little over 15 years. The topic of discussion for today is casing radiated treatment on air terminal units based on ASHRAE 130 test procedure. Before I get started, I want to, define a little bit further what we're talking about when we talk about an air terminal unit. In this case, some examples would be a VAV, a fan-powered VAV, a blower coil, a water source heat pump, a fan coil, things of that nature would fall into this classification and category. And as you look at a air terminal unit, right, there's a variety of noise transmission paths that can be present, shown in this illustration here. You can have casing radiated noise. You can have induction inlet, sometimes referred to as return noise, right? You can have induct noise from the fan if it's a fan power type of unit, upstream or downstream of the unit. You could potentially have breakout noise, right, upstream or downstream of the unit. And you could certainly have some noise at the diffuser as well if the unit's not properly selected for, the diffuser is not properly selected for the application and the type of the unit. So specifically today, though, we're going to put a focus on the casing radiated and the induction inlet, which I've circled in red. And just real quickly, there are some common treatments that people, you commonly see in the field that are used. Things like field lagging wraps around a unit, right? I've seen gypsum board enclosures around units. I've seen the use of increased mass in ceiling tiles, whether that's in the tile itself or whether that's some materials above the tile to try and help with address noise. Silencers, right? Line ductwork. There's a variety of traditional approaches that are taken to try and address some of these transmission paths. But again, our focus today is going to be on testing that was conducted for casing radiated and induction inlet. So there were four really goals of the testing. The first was to look at a comparison of engineered factory fit removable jackets or covers to field or site fabricated types of designs. The second goal was to look at the performance impact of treating the control box on a unit. The third impact was to look at the performance of changing the construction of the barrier septum in the jacket or sound cover itself, and looking and contrasting that with 1 pound per square foot versus a 2 pound per square foot density barrier. And then the fourth was to look at the cumulative performance of an induction inlet silencer with a removable jacket on the unit. So the testing setup and methodology, as you can see in this illustration here, was to take an air terminal unit. In this case, it was a series flow fan-powered air terminal unit with a 10-inch inlet, and to apply, as you can see by the illustration number 1, an acoustical removable jacket, and then also to take a look at a silencer on the induction inlet shown by item number 2. So the testing standards that were used were ASHRAE standard 880-2017, which is the performance rating of air terminal units, and ASHRAE 130-2016, which is the methods of testing air terminal units. ASHRAE 130-2016, the setup and configuration is shown in figure 2.0 on the left-hand side here, as far as the duct diameters, and other requirements for conducting the method of testing. And then the right is the test chamber that was conducted in. It was a NVLAP certified third-party lab. In this particular case and some of the other testing that I'll mention here, the induction inlet was blanked off for this particular test, okay? And then a calibrated broadband noise source was mounted inside of the unit to allow it to radiate through the cabinet of the fan-powered VAV unit. So again, the goal in the first comparison was to look at a engineered factory versus site fabricated type of design. On the left-hand picture, we have the site fabricated, which is very common that you would see. And on the right-hand side is a custom fit fabricated removable Velcro type of design. The table below shows the actual attenuation, the noise reduction that was measured. And you can see certainly that the factory engineered solution significantly outperformed the field site fabrication. It's important to note, that the factory engineered solution is specifically designed for the piece of equipment, right? To fit the dimensions, the penetration openings, and everything. That it's also a fully removable Velcro type of design with fully sealed corner strips, etc., that you can see in the picture to the right. The field is a very common, really was designed to mimic the contractor strategy, which is a low first cost, right? To take a, hey, here's a duct lagging material we have, let's apply this to the terminal unit. So, roll good material is cut to size. We did cut the material so that there was overlaps at the corners. Then typically an FSK type of tape is used to then seal that and to try and maximize the performance. We actually did do the site fabricated test twice. We felt a little bad about the performance the first time around, so we did a second test where we taped up all the edges and all the seams and everything else and saw no noticeable improvement in that design, but we did try and take a look at that. So from this testing, the critical factors that came into play was that it really is a function of the design and then making sure that the sealing of the edges and corners is done to maximize your performance. And then also, if you're going to apply a jacket to this type of piece of equipment, it has to be removable and reusable. It's not enough to just install it the first time if it's not going to be installed the same way the second time, or you'll never realize that overall performance down the road and in the future. The second goal was to look at the impact on treating the control box. On the left is an untreated control box unit, and on the right is a unit with a treated control box. Now, the reason to do this is that the control box on some units can occupy a significant surface area on a side of the unit. I would say in general, the control box is probably at least 50% of the area on one side of the unit. And as you can see in the table here, right, treating that additional surface area does have a noticeable improvement in the overall performance of the attenuation of the system. The third goal was to look at the impact of 1 pound per square foot and 2 pound per square foot barrier septums, right? To change the construction and increase the density to see if there was any difference. So just like the first two setups, this setup was exactly the same. A broadband noise was placed inside of the unit, and then exactly identical operating conditions, and the only difference was the change in the barrier septum construction. I've got two tables here, and let's just focus for a second down on the bottom table. That's the performance change in going from 1 pound per square foot to 2 pound per square foot. And basically what you see here, right, other than the 500 hertz, which is kind of a little bit of an oddity, right, there's no appreciable improvement in going from 1 pound to 2 pound. Now, right, we're often left to try and predict and estimate performance, right, of materials based on TL data. So the table above this one, I provided the TL data, right, based on ASTM E90 for these two different types of materials. And looking at that, we would probably, right, expect that the 2 pound would have some improvement over the 1 pound. But when actually tested, we didn't see any actual improvement in going from 1 pound to 2 pound. And it also, I think, is a little bit of a caution to be careful when we try and use TL data to predict the performance of different types of solutions on equipment. Now, left with nothing else, right? That is what we have to try and work with, and we have to do our best to be diligent and try and do that. But you can see that if you were to compare the TL values versus the couple slides back, the actual performance of a jacket type of system, right, the jacket performs significantly less than obviously the TL data, and that's due to flanking paths and other things as far as how it's actually applied and the difference in the testing standards. So just a word of caution there when you're looking at TL data and trying to use that as a predictor or estimator of performance. The final test was the cumulative induction inlet plus the removable jacket. So the conditions changed a little bit here. The unit was actually operated at 1.5 inches water gauge of inlet static pressure at 100% of its standard airflow. And then the external static pressure on the downstream duct was set at 1/4 of an inch. So the first pass, we took a silencer, mounted it to the inlet of the induction inlet, and you can see the performance there in the first row. Not real great in the lower frequency bands, and then certainly increases as we go up in frequency. The thing to keep in mind here too is a terminal unit typically cannot handle very much additional external static pressure, right? So your silencers have to be relatively small. You can't go and stick a 12-foot or 10-foot silencer on there, or you're going to stall the fan in the unit and cause some damage. So, typically a silencer is going to be maybe somewhere from 2 feet to maybe 4 feet in length is reasonable. And so, you're not going to get as much performance as you would expect, certainly in the lower frequency bands. The second application after the silencer was then to apply the jacket. That's the net increase. And then the final line then is the total inlet plus casing. So commonly from air terminal unit suppliers, you're going to see a row that says inlet plus casing. This would be a good representation on this last row of what that total inlet plus casing reduction would be if you applied both a silencer and a jacket to the equipment. So in summary, what is it we learned from the testing that was conducted? Well, first and foremost, that small gaps in field fabricated types of solutions have significant negative impact on performance. It's really not so much a function of the material, right? It's almost solely a function of how is it applied, whether it's 1 pound or 2 pound, or maybe even 3 or 4 pound if some future testing was done. The more, and I think all of us intrinsically know this, right? The more gaps and the less coverage that you get on a unit, the less performance you would expect to see out of that solution. This kind of goes hand in hand with the second point here, which is, treating all casing surfaces is needed to optimize the performance. Certainly, there was a noticeable improvement in the performance when you go and you treat the control box in addition to the rest of the cabinet. So potentially, you could also look at if the unit had a chilled water coil or a hot water coil, or something like that on the end of it. You may want to look at treating that. The more you can maximize the amount of surface area treated, the greater your overall performance should be for that solution. Third point, right, there was no noticeable improvement in 2 pound per square foot versus 1 pound per square foot construction, right? It just didn't show up in the data. It's not to say that maybe you could get a little bit more performance at 2 pound, and if you want to use that. But there are some design challenges as well with a 2 pound per square foot material. 1 pound bends fairly easily to make your corner seals and some other things like that. 2 pound does not bend very well and is going to be more problematic to make a good functioning design. I'm not saying it can't be done. It can. It's a little bit more challenging, and it's then a question of, okay, for the extra money to spend on 2 pound, are you really achieving any appreciable improvement versus using a 1 pound per square foot type of construction? Third point, the induction inlet and casing paths both show to be equally significant contributors. So it's important to make sure that you treat both paths, particularly if the terminal unit has an open induction inlet. Treating just the casing, right, isn't going to give you a maximizing of the performance. You really want to look at treating both of those. And then the last, again, just a cautionary statement here. Using ASTM E90 transmission loss data to predict performance can lead to sometimes some poor results. So just be careful if you're using TL data, particularly to estimate performance, because again, it doesn't really take into account leak and flanking paths like the testing that was conducted here. And you're going to get less performance than you really would expect if you're just looking at TL data alone. Possible future testing, if we want to take a look at that, could be the effect of the control box size on performance when treated and untreated. Again, what is the impact of the control box because of its surface area, depending on its size, maybe even where it's located on a unit. We'd also maybe take a look at repeating the induction and casing, but doing it in reverse order, right? Looking at putting the casing on first and then the silencer, see what we would expect the performance to be the same, but it'd be interesting to take a look at that. And then also look at the test variability of performance using OEM induction silencer options, things like lined inlets, lined plenums, elbows, T's, those types of things that are very traditionally used. So again, thank you for the opportunity to present, and I'd like to open it up for any questions.